Dear students, in today's video lecture, we will know about the homogenized form of transformation matrix. Of course, we will be talking of two-dimensional transformations. In previous classes, we have learned the basic transformation, that is translation, rotation, and scaling. As you know, the translation matrices, the translation equations are of this form, and similarly rotation and scaling matrices are of this form. The same transformations can also be denoted in the form of matrix like this. Here in case of translation, this is the translation matrix Tx and Ty, and it is added to the point matrix. Point matrix which is in the form xy, and it is added to obtain the new location of the point. Similarly, in case of rotation matrix, this is rotation matrix, and it is multiplied with the point matrix. And in case of scaling, it is a 2 by 2 matrix, and it is also multiplied with the point matrix. So as you observe them, uh, you can see that translation matrix is a 2 by 1 matrix, and it is additive in nature, means it is added to the point matrix. And the rotation matrix is 2 by 2 matrix, but it is multiplied, so it is multiplicative in nature. And the scaling matrix is also 2 by 2 matrix, and it is also multiplicative. uh, until now, when we were transforming in the basic mode only, it was okay. But in case of composite transformations, as we learn in future lectures, uh, a lot of transformations are applied simultaneously to a single point. So if they are not uniform in nature, they are not of the same dimension and of the same nature, it's going to cause a very big problem. So therefore, first before transforming in a composite way, we have to homogenize them. Means we have to change them into a similar kind, uniform kind of dimension as well as nature. So we will do it. First of all, we will change the form of a point matrix. Point matrix which was earlier xy. It was a 2 by 1 matrix, but it will be now x, y, and 1. It will be now a 3 by 1 matrix now. Uh, Next we go on to the translation matrix. So which was earlier a 2 by 1 matrix Tx and Ty, it will be converted to a 3 by 3 matrix. Its diagonal elements, these are the diagonal elements in which row number and column number are the same. Uh, the diagonal elements are taken as 1, and the non-diagonal elements are taken as 0. But these two elements in this matrix are taken as Tx and Ty. This is simple transformation of a translation matrix into 3 by 3 form. You can see now translation matrix will be a 3 by 3 one matrix instead of 2 by 1, and instead of being added, it will be multiplied now. Now let's move. This is the homogenized form of a translation matrix, and we now move on to the homogenization of rotation matrix. Before doing so, let's have a look at the translation operation, how it will take place. We will put a translation matrix and then multiply it with the point matrix, and the result will provide the new location of the point. So if you try multiplying these two matrices, you will get the same result as in earlier case. means you will get x dash is equal to x plus tx. If you solve this multiplication and compare this matrix, right hand side matrix on the right hand side with the matrix on the left hand side with corresponding elements, you will get x dash is equal to x plus tx and y dash is equal to y plus ty. And the third equation you get will be a trivial equation, 1 equal to 1, uh, no which has no importance for us. So we will use these two equations. So now let's move on the homogenization of rotation matrix. As you see, rotation matrix earlier was this: cos theta minus sin theta and sin theta cos theta. It will be now this. So instead of 2 by 2, it will be now 3 by 3. So cos theta sin theta minus sin theta and sin theta cos theta will be extended by non-diagonal elements 0 and diagonal element by 1. So it will be multiplicative in nature. Earlier also it was multiplicative, but this time also we will not change it. So rotation you can see as matrix equation in this form. So you place a rotation matrix and multiply it with point matrix. You will get the resultant matrix and compare that matrix to this matrix. So by doing so, you will get the new position of the original point after rotation through theta degree. So if you multiply it practically, you will get the same set of equations as in case of ordinary rotation. X dash is equal to x cos theta minus y sin theta, and y dash is equal to x sin theta plus y cos theta. And the third trivial equation, x1 equal to 1, may be ignored. Now let's move on to the scaling matrix, which is originally in this form. Sx and Sy are the diagonal elements and these are the non-diagonal elements. So it will change its form to a 3 by 3 form. So diagonal elements will remain as such and the third diagonal element will be 1, and padding non-diagonal elements will be 0. So you can see now the translation matrix is also of 3 by 3 dimension, which we had in case of translation and rotation also, and it will be again multiplicative in nature as in earlier case. So now if you use this in the equation form, it will be like this. You place the translation scaling matrix and then you place the point matrix in homogenized form and then multiply it after multiplication and comparison with the matrix on the left hand side. You will get values of x dash and y dash, which will be something like this, and it is no different from the scaling equations which we had studied earlier. So the third trivial equation can also be ignored in this case. So by now you have seen that translation matrix, rotation matrix and scaling matrix, all of them are now 3 by 3 having same dimension, and all of them are of multiplicative nature. So by doing so, we have changed all the matrices into a uniform 3 by 3 matrix which is multiplicative. So if we apply some of them simultaneously to a point, so it will be of the same nature and of same dimension. This we will study in the next videos when we study the composite transformations. Thanks for now.